Okay, so following straight on from the previous podcast on specific heat capacity, uh, this is basically a continuation looking specifically at measuring specific heat capacity. So applying the calorimetric techniques of specific heat capacity experimentally. In other words, how can we use this equation, Q equals mc delta T, or rearrange C equals Q over m delta T, in order to determine the specific heat capacity of a substance. Well, the substance that we're going to use in our example is water because it's easy to work with. There are a couple of different ways of doing this, but the way we're going to look at it is the electrical method. Now, we're going to be transferring energy to water. And a concept that you've encountered before is power. So power is the energy over time. Okay, so it's joules per second. It's given the symbol watts. Okay, so delta Q over delta T. So delta E is more generically energy, but in thermal physics, we generally refer to delta Q. So P delta T equals delta Q. So if you have a certain power, 10 watts for 10 seconds, 10 times 10 equals 100, so that's 100 joules. So you can replace delta Q in our equation with P delta T. So if you know the power of the power source, you know how many joules per second it's transferring, and you can time how long you're transferring that for, delta T, delta little t, the time taken, then you can put that in space of delta Q. So you have power multiplied by the time taken, delta little t, will equal the mass of the substance multiplied by the specific heat capacity multiplied by the change in temperature. Rearranging, therefore, C equals the power times the time taken divided by the mass multiplied by the change in temperature. So here we have the actual experimental arrangement. The water resides in a beaker here with a thermometer inserted, a stirrer to keep the liquid evenly distributed, and a heating element. So this is an electrical heating element which is powered by a power supply, which can be turned on and off, and there's a variable resistor which can change the current. And you measure the potential difference across the heater, and you measure the current of the circuit. Now, we haven't yet covered electrical circuits in any great detail, something you should have done in an earlier grade level, and in at least this amount of detail, but maybe you didn't. So the only equation that I'll have to ask you to take on trust now is that in an electrical circuit, a simple electrical circuit, the power equals the potential difference multiplied by the current. So if we measure the potential difference, which has units of volts, and we measure the current, which has units of amps, we can multiply these two together at any time, and that will give us the power supply. Obviously, this is assuming no losses, etc., which is why it takes place in a calorimeter. A calorimeter is simply the name we give to the device, the container in which this experiment takes place. And the idea of a calorimeter is it should be designed such that losses to the environment are reduced to a minimum. So there's a cap to prevent evaporation. There's two walls and a support to cut down on conduction, etc. Okay, so P, as I said, is equal to VI, so we can place that in the equation as well. Now, this is interesting. I've separated these out into MC and delta T because delta T is a variable, whereas M is a constant for this experiment because we're not changing the mass, and C is the constant because it's the specific heat capacity. And if we plot a graph of these two quantities, so V and I are constant, but over time, delta T, which changes, will produce us different values of delta big T, different values of change in temperature, and the gradient of that graph will give us the mass of the water multiplied by the specific heat capacity. So if we calculate the specific heat capacity, if we calculate the gradient, we can divide that by the mass, excuse me, to give us the specific heat capacity. Okay, actually carrying out the experiment, that's something that you will need to be doing.